Welcome to the Test of Time Awards. So it's a very great honour for me to have chaired the committee and to have had a chance to review some of the outstanding papers from 10, 11 and 12 years ago. So there were many highly impactful papers over that time period, but two stood out. One for the Research Track Award and the other for the Applied Data Science Track Award. So I could go into great detail about all the impacts that each of these papers have had, but I'm kind of hoping that the authors are going to tell you that. So I'll instead make way for them. So we have Stephen Scienna and Brian Perosi are going to present DeepWalk, Online Learning of Social Representations. Over to you.
Thank you very much. Thank you very much, and thank the committee for selecting us. You know, any advisor, when they talk about, stuff that the work they do with their students, they always are supposed to say, oh, my students, couldn't do it without them. They're the ones that make the work possible. This one, absolutely, the students did the work. This was one where I was fairly superfluous on. So it's been great to see all the reaction that DeepWalk led. Again, here we have Rami and Brian back in the days when they were in our lab. It was an exciting time in our lab when this was going on. We're proud that DeepWalk has had over 11,000 citations in the last 10 years. When I tried to do an analysis of all the papers on the ACM digital library that had mentioned KDD in it, okay, we apparently are fourth in citations among all the papers that had that, which I think is pretty impressive. And, basically a lot of the work in graph representation and learning, kind of makes this a starting point. So what was the idea of DeepWalk? DeepWalk was the goal was to try to learn a feature representation from graphs. And the idea is unbelievably simple. Basically, this was a time when word embeddings were kind of a big thing in NLP. And there was word2vec, which was this code that would take sentences and train on a lot of sentences and figure out what the words meant, gave a vector representation to each word. Okay, Brian and Rami's idea is that, if we treat a graph, the vertices of a graph like the vocabulary of a language, and random walks on this graph like sentences, then you can pump it through word2vec and you can come up with a representation for it. And, the amazing thing is this relatively simple idea works very well. And I certainly didn't really have an idea why this thing worked for a while until it kind of dawned on me that what I think was the important idea behind here is that this random walks thing gives you an idea to learn about what a vertex means from neighbors and distant neighbors without the cost of like raising a graph to a power, okay, which is an expensive operation and brings in lots and lots of edges and stuff like that. So my favorite example of something, of a DeepWalk, a graph we DeepWalked, okay, was I had a postdoctoral visitor who had access to the phone network of Belgium. And that meant who called who in Belgium for this particular cell phone provider. And this represents where each dot is a person in Belgium. We DeepWalked the call graph and slapped it down into 2 dimensions by TSNA. And then we colored people by what language they spoke. You had the phone network company said you could request complaint messages in English or Dutch or French or Flemish. And when you look at it, the amazing thing is, again, how well clustered it is. You can predict what language people spoke just based on what they were connected to. The time when I personally started really believing in this DeepWalk thing was we had a project with another grad student of mine where we were trying to analyze Wikipedia and try to figure out for each person, could you compare two people's Wikipedia page and decide that they're similar historical figures, okay? Maybe, who am I going to take a guess? Let's say you have Abraham Lincoln. You would like presidents of that time in history. Albert Einstein, similar figures are probably great scientists. So we built a test for kind of evaluating this. But the upshot was, by reading the text of Wikipedia, we could do pretty well, somewhat well, kind of well, at telling whether one person was similar to another person. Then Brian said, why are you bothering with the text? Why don't we throw out all the text and just use the connectivity graph? Which Wikipedia page is linked to which other pages? And when we did that, the DeepWalk result was better than all of our language analysis results. There seemed more information in Wikipedia if you throw out all the text and just keep the edges. I'm not going to go through that. Then, again, DeepWalk has been fairly popular. My sense, reading the papers, there were a lot of, one thing, because DeepWalk was so simple, there were lots of other graph embedding methods that came along that would slightly tweak what we were doing, and and come up with a new node embedding algorithm. And so there were dozens of these papers. The thing that I always liked is DeepWalk, to my memory, always seemed to come in second to the guy who wrote the paper's new method in every evaluation. Kind of it was amazingly. It's somehow very good and very robust and very simple. We still use this in our lab, and this is a good thing. And the final thing I want to say, just before going to Brian, is that one of the things that kind of, would be viewed as a descendant of the graph embeddings that kind of DeepWalk was, at the start of, were these are the graph neural networks, which are obviously very popular here and very important. If I compare graph embeddings to graph neural networks, graph neural networks have the advantage, in some sense, that they are trained in a supervised manner, so that they take advantage of other properties, not just the topology of the graph, but labels and other vertex and maybe edge properties. They enable you to kind of compute embeddings of things after the graph is built. So there's some level of, you can add new things to the graph, and you can do that, and that's something that you can't do very well with what we're doing. That said, there are some times when it's very nice to have an embedding. I think I like embeddings because they are things, and you can study things. Like we were studying what the language distribution of people looks like in Belgium. And for this, as well as the model building things, in my lab at least, we still do the DeepWalk. And I guess at this point, I'd give Brian the chance to go on and tell us what the rest of the world has done since.
Thanks, Steve. All right. So yeah, I mean, in some ways, I think Steve hit a lot of the high points already, but I wanted to kind of give my own take on it. And I guess the first thing I want to point out is that, like our, original proof of concept DeepWalk was done in a Jupyter notebook or something. It's got like 34 nodes in it. But nowadays we're still using DeepWalk, but we're embedding things with, this is like a 100 million node graph, but I mean, we go a lot larger. Actually, the hard part is not deepwalking the graph, but actually doing the t-SNE over the, to get the two-dimensional representation. So what I want to cover today is, I mean, kind of a little bit like what is DeepWalk, although we don't need to talk about that too much. Its academic legacy, kind of the industrial impact, and whether we should be talking about DeepWalk 10 years from now. So to start, what is DeepWalk? Steve covered this, right? It's just a widely used algorithm for graph representation learning. And I didn't come up with this myself. I just asked Google and then, decided that that was the right answer. Thanks the Oracle Help Center. So where did DeepWalk come from? I want to take you guys on a journey, right? Like we're going to go through time. That's what it looked like in 2013. There's Stony Brook, and we're going to go right through that portal. Neural networks are viewed with skepticism, because only a couple people are interested in them, and most of them are, I don't know, at Stanford or on the West Coast or something. And your advisors heard about neural networks in the 80s, and they didn't really work that well then, so why should they work now? It's the same words. It's understandable, right? And a lot of advisors had this opinion. And feature engineering, it's best done by hand, so you understand what the features are. The normal course of a PhD in the year 2010 was to get some data and look at it really hard and think really smartly about it, and then write some code to manually extract some properties of it and then put them in a feature vector. And then put a logistic regression model or something very similar on top of it. And so there were many hundreds, if not thousands of PhDs who did this kind of logistic regression journey. And they all have good lives now. They're all very prosperous. It's like don't worry about them. But it wasn't mentally satisfying, right? So there were hints at the time that things could be done better. There was this NLP from scratch paper that we found to be kind of very inspirational. And the idea there was you could learn one word embedding that you could do multiple tasks with for natural language processing. So this was kind of unbelievable at the time that you could learn one vector and then use it for part of speech tagging and named entity recognition and other stuff. I know it nowadays you're whatever, I'll just get my bird embedding and do it. But that was really state of the art back then. And then you kind of had things like ImageNet, right, where you could see the neural network feature extractors working over images for really amazing performance. And you're seeing people show you a 1 pixel of the neural network that was the cat identifier or something, right? So that you could really see the feature extractors working well. And as grad students, we really wanted to find a way to solve prediction problems for our advisor without spending so long on this annoying feature engineering, right? So we were desperate. And desperation breeds creativity. So let's get away from this world where we're looking at the adjacency matrix and we're trying to pull these features out, the degree of the node. Oh yeah, because we went back in time, I decided I'd just throw the original slides from the presentation there because this is how ugly all slides were 10 years ago. Thank you, PowerPoint, Bill Gates, and whoever runs Google Slides at our company. So this is the pairs of common neighbors. There were so many papers about these kinds of different link prediction features and different manual ways of extracting clusters and finding similarity between nodes. And every paper on social network analysis, which was very big in the late 2000s because of Facebook. That company's called Meta now, if you guys aren't familiar. Right. So so you'd take these features, you'd put them into a vector, and then you would run these tasks. You would kind of get rid of the graph part of it, but you'd get rid of it in this really manual way, and you do it different for every problem. Like Steve said, DeepWalk's idea was, hey, what if we could somehow learn this with the neural network? And because Steve just went over it, the idea is really straightforward. You take a random walks to turn the graph into a sequence, then you use sequence modeling, and then the output of the sequence modeling is something that understands local context in the graph very well. And so, I think that maybe, DeepWalk is an early example of convergence. I mean, we didn't think about it at the time, but what we did here is we used a model that was not designed for graph data at all to solve this particular problem. And this is it's an example of a very simple, if you want to call it AI, sure, DeepWalk is AI. It's an example of a very simple AI model that was, but it really did kind of transform how people started thinking about the, predicting things in graphs. And I think we see that, nowadays with even more powerful models can solve more powerful things, right? Transformer can do this. So I wouldn't say that we invented convergence, but if you want to take that away, sure. But we were definitely kind of inspired by this idea that maybe you could kind of transfer algorithms between problems. Now, once this paradigm took hold, we saw more and more models being applied to the graph domain. And like Steve said, there was kind of a pattern here, like a DeepWalk recipe that people could kind of play with very easily. You do some sampling, to turn a graph into, random walks. After you had the sequences, you could do kind of any sequence modeling, really. Like we use skipgram, but there's so many other choices possible. And then, the output, once you have this stuff in a latent space, you can kind of do with whatever you want with it too, right? So we looked at the node embeddings, but people also wanted embeddings of graphs and substructures and like more complicated things. I want to just call out the theory of DeepWalk that has kind of gotten better and better over time. That's just an idle random walk picture. So we started with like a very empirical result. We observed that it worked in the lab, and it seemed like it worked well when we did it on academic data sets, like social network prediction data sets. And then, for other stuff, like stuff our advisor wanted us to predict, it seemed like it worked for that too. Since then, there's been a much better understanding of why and how DeepWalk works. And this is some of it based on extensions of the theory for word embedding modelings, like Glove. So there's connections to kind of matrix factorization where you can think about factorizing the random walk transition matrix instead of doing the random walks manually. If you're going to look at the random walk transition matrix, you might think about the personalized PageRank matrix, and you can show that doing like a low rank approximation of the personalized PageRank matrix is pretty similar to a DeepWalk embedding. People have looked at the conditions under which you can learn, like what you have to have for that to happen, or the convergence bounds for community recovery. So we do know a lot more about why this works than we used to, but I would say that we still lack a total understanding of when an embedding is good and how to learn an embedding, which I actually think is kind of crazy because many people have been doing this kind of work for 10 years now, and it's still not totally solved. One kind of unsolved problem that I have in my daily life at Google is if I take an embedding, or take a graph rather, and I create an embedding of it, but I don't have any downstream task, it's very, very hard for me to tell if the embedding's any good or not. And this happens, you're like, why would you ever embed a graph without knowing whether it's good or not? Great question. But it happens all the time. People will give me their large, noisy graph. I'll embed it, and then they'll ask questions, then they'll try to decide whether it's good or not. So we'll have to come up with some downstream tasks. If we knew whether the embedding was good without the downstream tasks, we could save a lot of time. And so I think that, we have a paper on kind of like metrics for unsupervised embeddings, but I think that there is so much more to be done in this area. I think if we're going to talk about DeepWalk, we should talk about what people have done since, in brief. And so we had that kind of pipeline of, hey, you could change the sampling, or hey, you could change the model, or hey, you could change the granularity of the graph you're looking at. One thing we did, we looked at multi-scale random walks, another part of my thesis. There's a pretty popular paper that looks at kind of non-backtracking random walks. There's also a whole graph representation that people looked at, heterogeneous graphs. Like a hierarchy. Another thing we looked at in the lab was what if you looked at, used the hierarchy of the graph to help inform the embeddings. And so many more, right? There's, a ton. For anything I talk about here, there's just going to be a ton of papers. Similarly, with modeling changes, there's a ton of these too, right? Stuff like Line and grep and NetMF, each of them kind of using basically a different matrix factorization versus doing the PPR matrix, and so many more here too. There's way too many to list. But things that our group worked on, we first kind of looked at directed graphs because we wanted to look at, graphs that were, if you had a backtracking thing inside the structure of the graph itself, you'd want to follow the edges of user behavior, or something where you going backwards in the random walk really doesn't make sense. We looked at attention and in terms of adding attention, so you could actually learn what parts of the random walk to look at to reconstruct it. We looked at using multiple representations for different nodes. We also looked at removing bias from graph embeddings, and this is kind of like I'd say an understudied area. Like there isn't a lot of work in fairness or like bias-aware graph embeddings right now. And it sort of, I think, is probably pretty important, especially as we kind of put these things into recommendation algorithms, and like we're using them as features in all kinds of things, and they're useful features, but it's even more useful perhaps to control exactly what's inside the embeddings. And so that was one thing that we looked at several years ago now. Another really cool thing we looked at was how to compute an embedding one row at a time instead of needing the entire input data set. And so this was for like scalable applications, so it came out of like an industry need. But not a lot of methods kind of have that property where you can create a local embedding, like know where you should be in the graph embedding space without looking at all the nodes and get exactly the same thing. So that idea of like instant embedding was very impactful for us as at least product-wise inside the company. Although I don't think anybody's really cared about the paper, but this idea is cool. I think it goes, from there to talk about the academic legacy. So the impact in data mining. I was going to try and print out every paper that cited it and then like make a pile. I quickly decided that it was a better idea to generate a pile of pictures, save the planet. And so there were so many extensions proposed in 2015 to 2017. We had evaluation tasks that were, standardized as people figured out how to judge these methods better. Hundreds of papers were written on this topic in the 2016 to 2020 window on using kind of keywords like node embedding, network embedding, graph embedding, information network embedding. Like these are I would say the direct descendants of DeepWalk, and there's just so much. If we look at how DeepWalks and graph neural networks kind of interacted, there were a couple different trains in the literature. There were some kind of like, I'd call early graph embedding methods, like locally linear embedding. There were early GNN methods. Both of these, they were good in their own way, but there wasn't a lot that happened after the papers were written. I mean, LLE, there was a lot, but that was like in a different space, kind of for data visualization. It was really the kind of, out of the Facebook boom, we got these like latent dimension stuff from ASU, I believe. And so the social dimension papers, like they were kind of the closest like spiritual successors of DeepWalk, and I really have to thank them for making the data sets that we were able to evaluate on, because without them, we wouldn't have been able to do anything. So then DeepWalk came, and we had kind of a lot of papers appear, it's just a few of them, on the kind of the graph embedding track. But at the same time, people in the neural network and machine learning world were coming up with different ways of applying graphs to, kind of based on what convolutional neural networks were doing, but trying to generalize to like a non-regular grid. And so that, I think the best and most well-known paper was kind of the GCN. And once we got there, they started seeing some like pollination between these two areas, and then like I'd call it like the graph neural network explosion that happened with thousands, if not tens of thousands, of papers written on graph neural networks, applying them to every kind of problem and using them for just basically everything, right? I mean, there's so many interesting applications. To talk for a minute about industry and how DeepWalk was affected there. So, I'm gonna like say in my life, the big requirements for industry are, number one is that it just works. So this means the less hyperparameters you have, like the quicker you can get from data to a solution, like that time to market, is kind of like the most important thing. It's also important that it actually runs on your data set size. It's important that it runs with a latency that works for your application. But it's actually like a lot less important to have the best possible model. If you can spend one day developing something and it just works, you're not going to probably go back and rewrite it unless there's really big headroom to sort of spend more time on it. And so as part of the graph mining group at Google, like we focus on using graph structured data in all different sizes and scales of problems. So we're typically working with like billions, like applications that have billions of nodes or more and many more edges. And so when we do work, it's like we have kind of an algorithmic idea, we kind of have some like distributed systems and like some machine learning, and that's kind of like the intersection that we live in. We have a lot of applications across all kinds of Google products, and so like basically any product that you've heard of. In particular, like we have a subgroup that works just on graph embeddings because they're a very important part of our toolbox. A lot of times people have graph structured data, and what they want is they want to like basically encode that and then put it into some other model so they don't have to worry about the graph anymore. And so what we've focused on over the last 8 years is like iteratively creating techniques for embedding larger and larger models and doing it in less and less time. And so that's, I mean, it's, you definitely can still find problems in this area. We had a paper on this at KDD last year, it's worth noting. So I guess, other companies, right, like places where they have one graph that they care about a lot, I think of Meta/Facebook. They also have developed large graph embedding tools that are, if not spiritually inspired by DeepWalk, directly inspired. What they'll do is, one application that they've published on, they'll use these embeddings of basically different entities in the social graph. So it's kind of like a heterogeneous setup where you have users and posts, and users are interacting with pages, or stories, I guess, if they're on Instagram. And then they'll actually look for like abusive behavior in their users using those embeddings, and that's published paper we had actually at a KDD they had at a KDD workshop in 2020. So this is, I think, another, like, you see a lot of applications like this, at Google. I think any company that has this kind of like user interaction pattern is now using embeddings. Like a few other ones that don't have as many publications out, but we know that Amazon's using GDL. They have a big group that does graph stuff. Alibaba similarly has the library. There's some interesting references on fraud detection at like Ant Financial Services, Baidu. Pinterest is really big on graph neural networks. These have really become, like, I think, the dominant force for these kinds of models and recommendation systems in like large web companies. And then I think, to close, what's the future of DeepWalk? Will we be talking about it in 10 years? And I think the answer may be yes. Maybe not in exactly the same way, but the future is very bright. There's a couple key advantages, right? So although DeepWalk is the simplest GNN model, it's remarkably scalable, right? And there's always larger data sets out there to embed. And it's kind of like a good pre-processing step. So if you don't know what you're doing with your graph data, like step 0 to get a baseline is probably DeepWalk it or some similar network embedding and use that. There's a lot of interesting work on like graph neural networks where if you add node embeddings to them, they become more powerful. So this, DeepWalk and graph neural networks, I wouldn't say, like, sometimes they're viewed as competing, but it's very synergistic, right? You can always kind of add a network representation to your GNN, especially if you don't have a lot of other features. You'll get a lot of value of having it out of a unique node ID. And this is a frequent first step in many different kinds of like graph recommendation or node classification pipelines. And then I think, beyond that, like an active area of work in my group is kind of the intersection of graph structure and language models. And we're looking for graph embeddings that can improve generative AI's reasoning capabilities in complex settings. So we have this draft on archive about letting your graph do the talking, and it's basically kind of injecting a graph embedding, not learned through DeepWalk, but there's no reason why it couldn't be actually. And we show that when you can stick the graph directly in the token space of the model, you can really make the graph reasoning capabilities of the model a lot better. And so that's like, things like these kinds of applications, I think are gonna be with us for a while. I really want to thank my many, many embedding collaborators. There's so many that I probably forgot them while kind of listing them, like mentally. I also want to thank the department at Stony Brook and all of our friends and colleagues there. Thanks for attending the talk. I post papers on LinkedIn sometimes.
So we can take some questions if there are any burning questions in the audience. too good a job of explaining. I think he's a wonderful job of explaining both the approach and its significance. I think it's worth mentioning, we were chatting before the talk, and it was notable that the reviewers on the paper all gave it straight accept. There was no strong accept out of three reviews. So everyone thought it was solid, but not really outstanding.
Well, we showed them, didn't we, folks? Those reviewers are always wrong.
So I think we should all take heart from that, because we all get reviews that sometimes a bit pressing.
Yeah, while we're airing grievances, the test of time talk was the best paper talk was the same time at DeepWalk. So there were more people in this room than the original DeepWalk room. It's like nice to finally have an audience to give the talk to. Thank you all. I appreciate it.
Okay, so congratulations, and thanks for a wonderful presentation.
Thanks, Joe.
Very impressive. So next we have the Applied Data Science Track Test of Time Award winner, being presented by Yu Zheng. The paper is U-Air, When Urban Air Quality Inference Meets Big Data. Please join me in, again, congratulating them and welcoming them to the stage.
Okay. Okay, thanks for the recognition, and thank you for coming. This work was done when I was with Microsoft Research in 2013, and the second and third was the authors when my research interns working with me at that moment. Okay, air pollution was a global concern over 10 years ago. At that moment, the real-time information of air quality is very important to the protection of people's health from the damage of air pollutants, and also to the control of air pollution. Unfortunately, there are insufficient air quality monitoring stations that have been built in a city. For example, in Beijing, there are only 36 air quality stations have been built there, but Beijing is very big, okay? Because building and maintaining such kind of a station is very expensive. It needs a certain size of land and non-trivial money and the regular maintenance by people. So you can see they are not enough. Unfortunately, you can see air quality varies in location non-linearly and significantly. Here, each icon stands for one air quality monitoring station, and the number associated with each icon means the air quality index. The smaller, the better. The bigger, the worse. Different color denotes different level of air pollution. Green means good, yellow means moderate, red means unhealthy. As you can see, even at the same moment, two stations with very close distance may have dramatically different reading of air pollution. So this phenomenon is not a coincidence. According to the statistic on the data, okay, we do the statistic on the deviation of the air quality index reported by the 22 stations at the same time of interval over a period of 3 months. You can see the average deviation of the reading from the stations could be more than 70, and the maximum number may be 100. That's over 2 or 3 levels of different air pollutants pollution level. So to address these issues, we infer the real-time and fine-grained air quality throughout the entire city based on the reading from the existing station and combined with a variety of data sets we observe in the city, including meteorology, traffic, human mobility, point of entry data, and the road network data. So we deploy this technology to the Chinese Ministry of Environmental Protection. Here is the system we deployed. You can check the air quality of any location by just clicking on the map, even if there is no station built there. Okay, and this service has been deployed to cover 300 cities in China, helping 500 million people to get real-time information of air quality, and it saves over $1 billion for Chinese government. So this is a real system working, okay? And how does this idea come to our mind? There are two aspects of reasons. The first one is existing method cannot solve this problem very well. For example, there are some classical dispersion model in environmental science. They need to know the source of air pollution and then build connection between the source of air pollution and other factors like meteorology, traffic, which is very hard to get. And empirical assumption may not really hold in the real world. And satellite remote sensing can only get air quality of the atmosphere rather than on the ground. And it's also sensitive to humidity and weather conditions. And what if you use some cheap sensor? Some cheap sensor is portable, but it only works for sensing carbon monoxide rather than PM 2.5. The device for sensing PM 2.5 is usually big, not portable. And cheap sensors is not accurate enough, so it cannot be accepted by governments. And another reason is data-driven approach is ready, okay? We have a bunch of data observed in the city, reflecting the city dynamics, and they have been proved to be highly correlated to air pollutions, for example, meteorology and traffic. But the correlation between the data and air quality is very complex, much more beyond the empirical assumption. So it's time to use machine learning model to learn the correlation between the data observed and air quality in a city. So then we come up with this data-driven approach. Now we need to solve three aspects of challenges from our machine learning perspective. First, air quality change over location non-linearly and significantly. That means you cannot use some simple interpolation model to estimate the reading of a location without a station. And second, we only have very few stations generating air quality data. That means you have very few label data. So most of the supervised learning model cannot work very well. And I believe large language model cannot solve this problem very well too, because the data is very few. The data are derived from different domains, totally different domains. You have traffic data, you have meteorological data, you have pollen winds data. How can you identify discriminative features, and how can you fill knowledge from data across different domains? These are challenges. Then how we can solve these problems? Before solving this problem, we need to know how does air pollution arise from the environmental science perspective. First, the air pollution of a location comes from the local emission. That means the emission from the location. The second, there are also global dispersion. That means there are some air pollutants dispersed from its neighbor locations. And then they meet together, there could be some secondary chemical reaction. So you need to know the domain knowledge before designing your model. So we started this insight, then come up with our methodology. From a machine learning perspective, we can say the air quality of a location has a temporal dependency. That means if the current air quality is not good, then in the next few hours, the air quality cannot be good. And also there's a spatial correlation between air quality of different locations. Then the two perspectives or two views come together, have a mutually reinforcement between each other. So we translate the perspective from environmental science to our machine learning science. You can come back and say they are correspond to each other, okay? Then we can come up with our own models. So here, each circle means the location we're going to predict. White circle means the location without station, and black circle means the location with a station. So first of all, we have a temporal view to predict the air quality. That means we can predict the air quality from its own reading, okay? And also we can predict the air quality of the location from its neighborhood, I mean spatial view, right? So we have a temporal view and a spatial view. This is a multi-view learning, right? From our machine learning perspective. And remember, there's only a few stations generating label data. So it must be semi-supervised learning method. So we propose a multi-view based semi-supervised learning method to solve the problem. So here's how our model works. There are 3 steps. First one is do data selection and transformation. Second, do feature engineer. And third one, do a co-training based inference model. Oh, data selection I think is very important. So why do you seek such kind of data? First, point of which data, neural network data. So they are complementary of the traffic pattern and they indicate the land use of the city. And traffic data from taxi, actually we have trajectory generated taxi data indicating human mobility and traffic. And we convert data into the format that can be consumed by machine learning models. We partition a city into uniform grids, okay? And assume the air quality in each grid is the same, but air quality in different grids might be different. So in Beijing, we partition the city into 1 kilometer by 1 kilometer grids. So here, supposing this is a grid we're going to infer, so the air quality of this grid will be influenced by the data we observe in the grid and also the data of its 8 neighbor grids. So this is how we do the assumption. Then we extract 2 categories of features based on the data we collect in cities. So we partition the city into uniform grid. We project all of the data into the grids. For example, the project polling observation data, and we track pick up and drop off point from each taxi trips, and then throw the drop off and the pick up and drop off points into the grids. So this is how we do data transformation. Then we do feature extraction. So there are 2 categories of features. One is spatially related features. There are point of interest feature and neural network features. So you can see we calculate the distribution of POI over different categories because we have domain knowledge. We know what kind of POIs could generate pollutions. Okay, and we also count the number of vacant place. I mean, there's no POIs. So this actually is kind of a feature describing the land use. And also we calculate the change of POI in each category over 2 years. Some POI may disappear, some POI may be newly built. So, and also for neural network features, we count the level, the length of different level of row segments. And we also count the number of intersections. All of them are good complementary of traffic modeling. Because we cannot really get the emission from each traffic vehicles, so we can use the data to complement them. For temporary related features, there are feature extract for meteorological data from traffic feature and human mobility data. This is very interesting. Okay, you can see this is a correlation metric of features. Here, each row or each column stands for one kind of feature we extract from the data. For example, in the meteorological data, we have weather condition, wind speed, temperature, etc. Here, each plot indicates an instance we observed. It's an air quality index we observe in one stations. Green means very good. So as you can see, when the wind speed is very high, on this side is very high, so this is wind speed, we observe more green pollutes. That means when wind speed is strong, the air pollutants has been dispersed. So it makes sense. And when the humidity is higher, the air pollution is bad, okay? And also we can see the deviation of speed. So we partition a city in some uniform grid. So there are multiple levels of road segments located in a grid. We calculate the travel speed of each vehicles traveling on the road segment and calculate the deviation between the travel speed. So it's interesting discovery. You can see when the deviation of the travel speed is higher, the air quality tends to be good. Some people might think this is wrong, but actually this is correct. So that means without a traffic congestion, people may travel with very different speed on different level of road segment. You can drive very fast on highway. You must drive very slow on local streets. But if there is a traffic congestion, everyone has to drive in with a very low speed. Then the deviation between the speed is small. Okay. So when the deviation is high, you can say the air quality tends to be good. Okay. So we know everything we use is related. Okay. Then come up to the model. we come up with a co-training-based model, which is comprised of two classifiers. One is a spatial classifier, taking into account feature, spatially related feature, extracted from point matrix data and the row level data to encode the spatial correlation of air quality between different locations and model the global dispersion of air pollutions. Another one is a temporal classifier, taking into account the feature extracted from temporally related data like meteorological data and the traffic data to encode the temporal dependency of air quality in one location and modeling the emission from one location. So actually, it's very neat, very simple. And people ask me, how do you come up with this idea? Actually, this idea came from my dream. There was one night I get a dream, so I saw this problem in my dream, and I laughed out, awakening myself, and I get up and write down the idea quickly and publish the paper. So then we get the award. This is a true story, okay? So the idea is very simple. It's not necessary to introduce each of them. The temporal classifier is based on the conditional random field, with each hidden node denotes the air quality of the location, and the white circle denotes the feature we extract in each timestamp. Okay, and for the spatial classifier, it's comprised of two parts for data feature generation and for classifier. Here is very I think we need to mention this idea, okay? Because the spatial features are static, if you throw them directly into a machine learning model, you will learn nothing, okay? So here is how we do. We pair the location we are going to predict with three stations we have readings. We calculate the difference between their spatial features. For example, calculate the Pearson correlation between the distribution of POI in that location and the distribution of POI in this location. We calculate the difference between the spatial features. And through the difference, compared with the air quality of the reading from the existing station to predict the air quality of that location. We do such kind of pairwise training multiple times to learn the difference of spatial features and send them to the models, okay? Okay, how is the work is training? It's a very simple idea. We train this model with label data separately, and then use the two classifiers to predict the unlabeled data separately. And then we bring back the predict instance with very high confidence and bring them back to the training set. Okay. We do them separately until all the unlabeled data has been used out, or the prediction efficiency does not improve anymore. Okay, in the inference process, we extract feature from each instance and throw them into two classifiers separately and find the level of air pollutants with a probability production maximization. So this is very simple idea. Okay? We evaluate our model with the data from 4 cities. At that moment, we don't have 4 cities. And the amazing thing is we get an improvement on accuracy of over 20% beyond classic dispersion model. So this has been used for over 30 years in environmental science. They have been in a bottleneck for over 30 years, and this new technology has made a breakthrough of the bottleneck and bring over 20% improvement on them. And this is not the end of the story. And later on, the Environmental Protection, Ministry of Environmental Protection asked us, if you can do forecast rather than real-time prediction of undeployed location. So here, the next step, we do air quality forecast for each station over the next 48 hours. For the next 6 months, we do a prediction for each hour. And for the rest of the time interval, we do a maximum span prediction. But the additional unique challenge of this forecast is how can you forecast the inflection point, I mean the change point, you can see. If you can predict the inflection point in a stock market, I think you'll be very rich. But this is very hard because the instance is very, very few, okay? And luckily, we get some insight to solve this problem, and not 100% solve. I think improve this solution, okay? We published another paper on KDD2015. And this is another service we deploy with Chinese Ministry of Environmental Prediction. Here you can see the forecast of air quality of each existing station of next 48 hours. You can check the forecast of 6 kinds of air pollutants. The overall accuracy is about 800, and the prediction for the inflection point is about 48. Without our model, the prediction accuracy for inflection is less than 10%. But this is very important for government policy making. So if we know the air quality is going to be good tomorrow morning, so we will release the traffic control, and we can let people go outside. We can have our school started as normal, okay? And we'll save $10 billion per year for Chinese governments. So this is the original how our model looks like. We have a spatial predictor, we have a temporal predictor, and then we have a dedicated inflection point predictor. That means we predict them spatially, temporally, separately. We combine the result together, and there are some properties will trigger the prediction of the inflection point prediction. We'll generate another data and combine them together. This model works really well, based on the deep understanding of the problem we are going to solve. And then later on, 3 years later, our students come up with another paper based on the deep neural network to predict air quality. Actually, it gets some improves, but it's not that significant. Only a few percent, okay, less than 5% improvement. And the data transformation part is the same, okay. So later we influence our model, we evaluate our model based on the 10 cities, mega city in China. And we can see the improvement of the air quality based on deep neural network is about 80%. And the inflection point is 17 or 47% accurate. Without our model, it's only less than 10%, okay. And this is how our air quality looks like after 10 years of hard work fighting with air pollution. This photo was just taken 3 days before when I was leaving for this conference. We have been working with this area for over 10 years, starting from 2012, and still working on this part of research. 3 lessons to learn. First of all, we need to analyze the problem thoroughly so as to incorporate domain knowledge into our model. You can see how we design model. It's not very complex, but with the domain knowledge. Okay. And second, understand the data very well so that you can use the data generated from one domain to solve the problem in another domain. This is a very popular word recently, cross-domain knowledge fusion, or knowledge alignment, or model alignment. All of them based on the understanding of the data. If the data cannot be aligned, so you should not throw them together, okay? Third one is deploy our technology to the real world, and you will continually find new problem to solve, and you get values from the society, okay? So that's all. Thank you for your recognition, okay?
Do we have questions? I have one question. I was very curious about how you evaluated the system. So you did leave one out, cross-validation on your labeled data points, but my presumption would be that the places where the air quality stations are a very biased sample of all locations, and so I would not expect it to generalize well to other places.
Yeah, for the first piece of work for real-time and fine-grained air quality inference, so we can remove one station. Supposing we have no idea of the reading of this place, and then we use the reading generated by this station as a ground truth to evaluate the prediction. So we do such kind of removement randomly multiple times, okay? And you do such kind of evaluation across multiple cities. So you have a bunch of ground truths to evaluate. For the second piece of research, it's easy because after you have historical data, you know what air quality looks like, and you know you can measure your prediction against the historical data for the evaluation. Yeah.
But aren't the places where the stations are located typically places where pollution is expected? So other locations will have different patterns, I would have expected. So I was wondering how you kind of evaluated how well they work, how well your predictions work in other locations.
Right. This is based on the spatial predictor. Actually, why we need to pair this place with multiple set of stations? Because different stations may have different land use or distribution of POIs. So if you only select one set of station to pair with this location, then you could not know how different location would have different air quality pattern. You can see we pair them differently. And so this is actually learn the spatial correlation of different land use, different spatial features. So we do the training based on the data from the station. We pair them into multiple sets, do thousands of training, then you learn the difference, okay? And also we have a research paper to guide the government to where to deploy a new station. So here is the tension. If you can predict the location of a place with a very high confidence, that means it's not necessary to place a new station here. If the confidence is very low, then we need to build a new station there. Oh, I forgot to add them. Actually, it's also a paper published at KDD. Yeah. So Xunping is also a co-author of that paper. Yeah. Yeah.
I have a question here.
Every time I read this paper, I have new understanding. So for this problem, you have setting it as a classification task. So if we want to infer the exact value of that place, so it is a regression problem. So if we want to leverage central machine learning, I think we cannot directly doing the product between the probability of that equations, right? So do you have any idea over it?
Yeah. At that moment, actually, predicting a real value is more complex than predicting the level of air pollutions. Because at that moment, we have very few data sets. We only have data generated by 36 stations of over 2 years. You can say every 1 hour have one instance. 36 instance for 1 hour, and you have only very few training set. So at that moment, we select to predict the level of air pollution. Okay? But you can do with more data, you can predict the real value. And you can change the model a little bit. Actually, for example, it's not necessary to use a conditional random field. What if you use a linear regression or other regression model, okay? And also there are some regression tree you can use. But based on the understanding of the knowledge from the domain, it's very important. Why you use this model? Why this model can solve this problem? Why can them combine together? I think this is more important than this model because today we have many advanced models. You will not use this kind of model itself, but the insight you can leverage, right? Okay.
I have a medical question to the two authors, really. If the two authors of the test of time will have no idea of the paper and the problem, how would you think, would you use it, if you use DeepWalk on this problem and change the grid-wise representation to a graph-based representation, how would that actually change potentially the result, or if that's even visible at the time? And I will also ask the same question to the people authors. If, for example, the aspects of the sparsity and dynamicity in this kind of problem actually is actually kind of intractable for the DeepWalk. So my last question.
Who is first? You go first.
Ryan may have smarter things to say. mean, when I'm hearing this, I'm thinking the graph here would be representing your spatial features, and that, and we would be living in a world of a relatively static graph. So we would learn that places that were next to each other were next to each other, or that places that were, so it's, it seems to me that this is more a geographic, it makes sense that you were thinking of this in terms of geographic regions and stuff like that. So it's not clear we needed to talk to each other back then, but.
Yes, that's a good question, okay? Of course, we can use graph embedding and graph, because neural network is kind of graph. And if you treat each station as a node, you can build connection between different nodes, okay? It's also a graph. It's also a dynamic graph, spatial temporal graph. In our area, it's actually called spatial temporal graph. I think it's a new topic we can do in recent years. How can we encode the spatial temporal data while preserving its spatial temporal properties? If we throw them, for example, if we simply throw a neural network into a graph embedding model, the spatial property and temporal property may be lost. That means the two nodes in geographic space that are close to each other may not be close to each other after you do embedding. So how you can ensure the geospatial distance after doing the encoding is, I think, a new research topic you can do. And how you can, second topic is how we can combine spatial temporal data with text image data. They are totally different multimodality data from different domains. So my answer is do knowledge alignment. So if you know there's some point you can find the alignment on the knowledge level, so you can combine the three different kinds of modality data together. For instance, if you know someone lives in a place, you might have three different types of data observed in the real world. One is you have some image or video shots he taken around his home, okay? Or he posts some tweets on Twitter, you can see some tweets. This is the first type of modality data. And also you can observe GPS trajectory generated by these guys. And then you can analyze his living place, okay, by doing stay point detection and doing geocoding, reverse geocoding. And also you might have some spreadsheet data. He filled in online forms when using some e-government service. You fill some online form. You accurately tell the government your address, right? So the three type of data looks very different, but it can be aligned in high level of knowledge. The knowledge that lives there. So you can combine the three type of data together to infer his location, infer his home. So that is new, I think it's a new topic of research direction. Multimodality data or knowledge fusion across different domains. So multimodality, multi-domain knowledge fusion. So that's my answer. We can collaborate. Okay.
So please join me in thanking Eugene for and congratulating Eugene and his team for this fantastic award and for a fantastic presentation.
Thank you.